Hello, everybody. This is Bert Dixon here presenting today on lesson 8.3 on trigonometric integrals. So this lesson focuses on really any integral that has a trig function inside it and different approaches that we can use for evaluating those integrals. So there are some trig integrals that we already know how to evaluate. For example, this one, secant squared, the integral of secant squared we know is tangent. So what are some other integrals that we already know how to evaluate? Let's see, we know the antiderivative of sine x dx. The antiderivative of sine x dx is negative cosine x plus c. We know the antiderivative of cosine x is sine x plus c. Some others that we have derived earlier on, back in the 7.2 notes, we derived this one, that antiderivative of secant x is the natural log of the absolute value of secant x plus tangent x. And then in the, whatever the section, the natural log, when we learned about taking derivatives and integrals of natural logs, we learned that the antiderivative of tangent x is natural log of secant x. Okay, so those are some of the basic ones that we already know and have derived earlier on. So we're going to use these kind of as a basis for ones that we know, and then if we have some more sophisticated integrals, we want to eventually reduce them to one of these 5 integrals. And so this table gives you kind of a strategy if you have powers of sine and cosine inside an integral. So sine to the m power, sine to the m, and cosine to the n. This gives you step by step what to do. So if m is odd, then it's suggesting that you you use this identity, sine squared equals 1 minus cosine squared, to break up the sine squared into break up the even powers of sine and write them as cosines. And so we'll definitely do some examples of that. And then if n is odd, then you can follow this. And then if neither one is odd, that means both of them are even, then we can use these identities. So these all come back to using the trigonometric identities and the double angle identities that you've learned previously. And this table is on page 461, by the way. If you have a hardback textbook, you can just refer to it there. This is the same exact table, so you don't need to write that down. All right, so let's take a look at example 1. So in this one, I noticed right away that I have sine to an odd power. So we'll follow the first suggestion, which is use sine squared x equals 1 minus cosine squared x. So I'm going to first write this as sine to the 4th x times sine x times cosine squared x dx. And so now that we have an even power here, we're going to write that as, let's see, that's going to be sine squared x sine x times cosine squared x. Then each of these sine squareds can be written as 1 minus cosine squared, as was suggested up here. Case 1 says use this identity, sine squared x equals 1 minus cosine squared. And so each of the sine squareds I'm going to replace with 1 minus cosine squared. Okay, and then what we can do is do a substitution and say u is equal to cosine x du equals sine x dx. So this sine x dx is going to get replaced by du, and then the rest of it is all cosines. So this is 1 minus u squared, 1 minus u squared, and then this one is u squared. And so if I simplify all that, that ends up being negative, let's see, we would end up with negative u squared plus 2u to the fourth plus or minus u to the sixth du. It's because I left the negative sign off here. The derivative of cosine is negative sine, so then this should have been negative out in front of this integral, and so if I distribute that through, I end up with this integral, and then the antiderivative is going to be negative u cubed over 3 plus 2u to the fifth over 5 minus u to the seventh over 7, evaluated from, oh, we don't have any endpoints. And so now we can just plug in cosine for all these, and we get negative cosine cubed x over 3 plus 2 cosine to the fifth x over 5 minus cosine to the seventh x over 7 plus c. Okay, in the next example, it says here, if m is odd, we do case 1. M is not odd, m is even. So then we go on to case 2. N is odd. And so this time we're going to do kind of the same strategy as what we did, but we're going to break up the powers of cosine into an even power times a single power of cosine. And we're going to use this identity. Cosine squared is 1 minus sine squared, so still using the same Pythagorean identity. So then this is sine squared x cosine squared x cosine x dx. And then we're going to rewrite this cosine squared as 1 minus sine squared. And then do a substitution. U is equal to sine x du is equal to cosine x dx. And so that gets replaced by du. And then this is going to be u squared times 1 minus u squared, which is u squared minus u to the fourth du. And so then that is u cubed over 3 minus u to the fifth over 5 plus c, which is sine cubed x over 3 minus sine to the fifth x over 5 plus c. Okay, I'll let you go ahead and try C. In this one, both M and N are even, so you're going to use case 3. So pause your video, try that one out, and press play when you're all done. Okay, so for this one, we're going to replace sine squared with 1 minus cosine 2x over 2, and cosine squared is 1 plus cosine 2x over 2. They're still inside the integral, so now we need to evaluate that integral. If I multiply these out, I end up with 1 minus cosine squared 2x over 4. And this can be broken up into two different integrals. We can write this as integral of 1/4 dx plus the integral of, or minus the integral of cosine squared 2x. We'll put the 1/4 out in front, so minus 1/4 cosine squared of 2x dx. And the first integral is just 1/4 x. The second integral we can write, we can use the same identity we did before, so that's going to make this 1 plus cosine of 4x over 2. And then it's more of the same process. So now we have minus 1/8 integral of 1 dx, or let's just say 1 plus cosine of 4x dx. And now we have an integral that we can evaluate. So this is 1/4 x minus 1/8 x minus 1/8. This would be sine of 4x over 4 plus c. And that should be it. Actually, we can combine these together. 1/4 x take away 1/8 x is just 1/8 x. And then this would be 1 over 32. We can call it sine 4x over 32 plus c. And that's a more simplified answer. Okay, and then part D is also even exponents. This one's a little bit harder, so we'll work through this one together. It's going to start the same way as we did our last one. We're going to replace sine squared with 1 minus cosine 2x. So this is going to be 1 minus cosine 2x over 2, but it's going to be squared because sine to the fourth is the same as sine squared squared. And then this is going to be 1 plus cosine 2x over 2. And so now if we split this up as 1 minus cosine 2x over 2 times 1 minus cosine 2x over 2 times 1 plus cosine 2x over 2. The reason why I did that is because now I can multiply these two that are conjugates, and that'll look a lot like what we had in the last problem. So we'll have 1 minus cosine 2x over 2, and then the product of these is going to be 1 minus cosine squared of 2x over 4 dx. And now, just like we did in the last problem, we can rewrite this as 1 minus sine squared. So going up here, I'll have the integral of 1 minus cosine 2x over 2. In fact, let's pull all the denominators out in front. We'll call it 1/8. 1 minus cosine 2x times sine squared of 2x dx. And then that is sine squared of 2x, so I'm distributing here, and here, so that was sine squared of 2x, and then minus cosine of 2x times sine squared of 2x dx. And I'm going to split that up into two different integrals so that I can use substitution on this one. And so now we have 1/8 integral sine squared 2x. I'm going to write as 1 minus cosine of 2x over, or actually of 4x over 2. And then minus 1/8 the integral of cosine 2x sine squared 2x dx. Okay, and then this one I'm ready to evaluate. This is going to be 1/2 x minus sine of 4x over 8. And then this part, I'm going to use a substitution. We'll say u equals sine of 2x du equals 2 cosine 2x dx. And so that means cosine 2x dx is going to get replaced by 1/2 du. So here we have cosine 2x dx is going to get replaced by 1/2 du, so that becomes negative 1/16 integral of u squared du. So just simplifying all of this now, we have x over 16 minus sine of 4x over 64 minus u we said was sine, so that's going to be sine cubed of 2x over 48 plus c. Okay, go ahead and pause your video and try problem E on your own, and press play when you're all done. All right, so for this one, since m is odd, we are going to replace, we're going to break this up into even powers. So we have sine squared x times sine x times cosine x dx. And then the sine squared, just like we did in the first problem, is going to get replaced by 1 minus cosine squared. And then I just reversed these. So that'll make it easier for distributing now and for substitution. So when I distribute the cosine, I now have cosine x minus cosine cubed x sine x dx. And so we're ready for substitution now. So u equals cosine x du equals negative sine x dx. And so this is going to get replaced by negative du. And then this will be u minus u cubed du. And so then we get negative u squared over 2 plus u to the 4th over 4 plus c, which would be negative cosine squared x over 2 plus cosine to the 4th of x over 4 plus c. Okay, so in all of the previous problems, we used several different identities. We used variations of the main Pythagorean identity, and then we also used this one and this one, and some other Pythagorean identities I've mentioned before. You can get to these Pythagorean identities from the main one by dividing. So, for example, if you start with sine squared x plus cosine squared x equals 1, if you divide everything by sine squared, then you get 1 plus cotangent squared x equals cosecant squared x. If you start with the main Pythagorean identity, but this time we divide everything by cosine squared, then the first one is tangent squared plus 1 equals secant squared, and so that's where this one comes from. So this one is here. So all the other two Pythagorean identities easily come from the first one. So if you just memorize that one, you can always get the other two if you forget them. Okay, so we're going to use these identities to try to rewrite some more integrals, different style than the ones this time. We're not looking at powers of sine and cosine like we were in examples A through E, but these identities can still be helpful. For example, here in A, we have 1 plus cosine of 6x. So taking this identity, if we adapt it, since there's a 6x here instead of a 2x, we could say cosine squared of 3x equals 1 plus cosine of 6x over 2, because this quantity doubles when you put it there. Okay, just like this was an x, now it's a 2x. Okay, so this is just a variation of that formula. And so now if I multiply both sides by 2, I have 2 cosine squared 3x equals 1 plus cosine of 6x. So now in this integral, I can replace the 1 plus cosine of 6x with 2 cosine squared of 3x. And so that's the same as the square root of 2 times this integral of cosine squared 3x. And since we're taking the square root of something that's being squared, we just have the integral of cosine of 3x. And that is sine of 3x divided by 3 plus c. Okay, try something similar on problem B. So pause your video and try that one out. Press play when you're all done. For this one, we can use this Pythagorean identity and replace cosecant squared with 1 plus cotangent squared. So this is going to be cosecant squared gets replaced by 1 plus cotangent squared of 3x minus 1 dx. And then the 1 and the minus 1 cancel. So now we just have the square root of cotangent squared, which is just cotangent. And then the antiderivative of cotangent, we can go back to the way that we learned to integrate tangent, and that was by splitting it up as, in this case, it would be cosine 3t over sine 3t, or 3x, and do a substitution. So u equals sine of 3x, du equals cosine 3x dx times 3. So that would be 1/3 du replaces cosine 3x dx. And so now our new integral becomes, so cosine 3x dx gets replaced by 1/3 du. And then we just have 1 over u. So that's 1/3 natural log of u plus c. And that is 1/3 natural log of sine of 3x plus c. Okay, and then in example 3, this time we're going to use the Pythagorean identities to try to break these up into smaller powers. So for example, tangent to the fourth, if we break that up into tangent squared times tangent squared, then replace one of them using the Pythagorean identity that we have up here. Tangent squared plus 1 equals secant squared. So this is going to be, this tangent is going to get replaced by 1 minus secant squared. This one's going to stay here. And you'll see why we want to keep that tangent squared there in just a minute. So now if we distribute we have tangent squared x minus tangent squared x secant squared x dx. In this step, when I did this substitution, I actually have this backwards. This would be secant squared minus 1. I'm sure some of you caught that. So it's not 1 minus secant squared, it's secant squared minus 1. So then when I distribute here, it's going to be secant squared x tangent squared x minus tangent squared x dx. And then if we say, let's break this into two different integrals actually. So for the first integral, we'll say u is equal to secant x u equals tangent x, because the derivative of tangent is secant squared. And so then this is the integral of, so secant squared x dx gets replaced by du, and then we just have u squared, so we get u cubed over 3. And then this integral, tangent squared, we don't know an antiderivative for tangent squared, but I can rewrite this as secant squared x minus 1. And now we do know the antiderivatives. The antiderivative of secant squared is tangent. And the antiderivative of 1 is just x. It's going to be a plus 1 because if I distribute this negative sign, it's going to be plus. We have plus c. And then u, we said, was tangent. So this is tangent cubed x over 3 minus tangent x plus c. Okay, and for the last problem for today, go ahead and pause your video and try this one. Okay, for this one, we can break secant cubed up into secant squared x times secant x tangent x dx. And this one doesn't require any trig identities. We can just use substitution immediately from here because of the secant tangent that we got when we did that. We can say u is equal to secant x, du is equal to secant x, tangent x dx, which is exactly what we have here. So this is going to become du, and this is going to be u squared. And so then we just get u cubed over 3 plus c, which is secant cubed x over 3 plus c. And that's it. That's it for the notes. From the practice problems, all of these are pretty good problems. In particular, you can try number 12, number 20, and number 24 as a minimum. And the answers for those after you try them, number 12, the answer is 1/12 sine to the 6th of 2x minus 1/16 sine to the 8th of 2x plus c. Number 20, you should get pi over 2. And number 24, you should get 2 root 2. So go ahead and try those at some point and check your answers with these. Have a great day, everybody.